Welcome back. In our last video, we were talking about incidence rate and mortality rates. And when we looked at mortality rate, it is the incidence of death. So you take the number of persons who died in a year, divide it by the number of persons in the population, and that will give you the incidence rate. You choose your per 1,000, 10,000, 100,000 people, whichever is most appropriate to the number of the people in the sample, and you come up with your rate. So with mortality, the question I would want to know if I got a disease is, will it kill me? And so what we do is we look at what we call a case fatality rate. And this is looking at if you get the disease, will it kill you? And again, this is looking at data. It's not predicting 100% that you'll die, but it's just looking at in overall the number of people who get it, how many of them do pass away. So as a rough example, here is a chart. Here is a picture. You have a male on one side and a female on the other. And then what you have is here you have some types of cancer. You have the estimated new cases, and you have the estimated deaths from those cases. So here you have men and here you have women. So to compute the case fatality rate, you would take the number of deaths divided by the number of people at risk of death. So that would be for prostate cancer. If you want to find out what the case fatality rate is, this is the number of people in the at-risk population. They have the disease. This is how many passed. So you'll take 27,050 and divide it by 218,890, and then I would multiply by 100,000. And when you do that, you get 12,376 deaths per 100,000 men. So as you look at this, you think, well, prostate cancer, that gets a lot of press and we should be concerned about prostate cancer. And while I'm not saying we shouldn't be, if you now compute for lung cancer, you'll find that where prostate is 12,000 men per 100,000 men, lung cancer is 77, almost 78,000 per 100,000 men. So the death rate, the case fatality rate for lung cancer is much higher than it is for prostate cancer. So now do the same calculations for women, for breast cancer, and then for ovarian cancer. For breast cancer, I calculated 22,670 per deaths per 100,000 women. And for ovarian cancer, I calculated 68,123 per 100,000 women. So ovarian cancer has a higher case fatality rate than breast cancer. And we do know that the survival rate is lower for women who are diagnosed with ovarian cancer. Death rates are important. Case fatality rates are also very important. So let's move on to the next measure, which is prevalence. Prevalence measures the number of individuals who have a disease at a particular time. So whereas with incidence you were looking across a whole year, this is a snapshot. You want to know how many people have the diseases at a particular time, and that is called prevalence. So incidence and prevalence can be used to assess the total burden of a health problem in a population and can help identify the needs for services or intervention. So this tells us what portion of individuals in a population has a disease. So to calculate prevalence, we take the number of people living with a particular disease and we divide it by the number of people in the at-risk population. Here's our practice. We want to know the prevalence of obesity for the Irvine School District as of May 1st, 2017. There are a total of 15,000 students on May 1st, 2017. We asked the health officials how many students are obese, and obesity was measured by BMI, with a BMI over 30 kilograms per meter square being used as a criteria for obesity. They tell us there are 425. So again, you take the number of people with the disease and you divide by the number at risk. So in this case, we're going to take the 425 and divide it by 15,000. And again, because the number's a little smaller, I'm going to multiply by 1,000 and I get 28.3 students. And again, we're going to round up, so we would really report 29 students per 1,000 are classified as obese. If there's any part of this that you don't understand, let's talk during an office hour so that I can clarify anything that's confusing to you. So let's look at an example of the use of prevalence to identify problems. This is looking at the prevalence of obesity in the United States, and on the top we have 1990, followed by 1995, 2000, 2005. Across here is the key. You can see that if the state is white, there's no data. This light blue is less than 10% of the population was classified as obese. Here's 10 to 14, 15 to 19, 20 to 24, 25 to 29, and greater than 30%. So what we want to look at is what is the prevalence and how is it changing. So in 1990, you can see there were a few states that didn't have data yet. This is something that I pulled from the CDC website. So it was a new surveillance, a new monitoring, and you can see that there are some states like California had less than 10, and that a few of the states it was 10 to 14. But what you should notice, well, what do you notice? 1995, first of all, there aren't any light blue states. And now there's another category, this darker blue, which is now 15 to 19% of the population is obese. Move to 2000, we now again don't have any of, we only have one state that's this color, the rest are the dark blue, and we now have this kind of tan color, which means 20 to 24% of the population are obese. And then here in 2005, we have only Colorado, and I know that this was quite a bit ago. There are some more current slides, but I'll tell you, it just gets worse. Here you have a couple of states. Now if you look, and we will go look in just a minute, they're all red. So here's the current map. Told you it doesn't get better. There is no green, this color. Colorado is now at the 20 to 25%, but you can see a large part is greater than 35%. Previously, the dark red was greater than 30, if you look at this. So as you look over time at the prevalence rates of obesity, you can see that Americans are getting fatter. Here's some more data. On the left-hand side, we have the number of deaths for different occupations. And when you look at that, you might say, wow, a lot of transportation workers die. And these are on the job deaths. Looks like utilities is really safe. It looks like utilities is safer than education. And mining, construction and transportation look really dangerous. Like, I don't want to do that. A lot of people die on the job. However, if you look at the death rates per 100,000 workers, the picture changes. Whereas here it looks like, you know, what's up with education? Here, very few in education die on the job. Government looks like a lot of people die on the job. Here, very few. If you look at death rates per 100,000 workers, it's less than mining, whereas mining has fewer deaths overall. So when you look at data, you need to make sure you read to see what you're actually looking at. So this is just total deaths within the occupation. This is deaths per 100,000 workers. And this takes into consideration how many people are employed in that job. So, for example, there's probably a lot of people employed in construction, so you have a lot of deaths. But if you look at it per 100,000 workers, it's not quite as bad as you think. So, when we look at data and we see changes, we have to ask ourselves, is this a real change or is it artifact? Sometimes changes are not real. One of the sources of artifact can be an increased interest in identifying the disease. Sometimes there are people who become interested, or we find that there's a population that is developing a disease, and so more people start to look for it and research is done, and it looks like that there's an increase in the incidence, but it's just that we're looking for it. Another source of artifact is our ability to identify the disease, meaning if we develop additional diagnostic tools that help us find people who have the disease, that will increase the incidence and it may be considered an artifact. And another source of artifact has to do with changes in the definition. Things like autism have been redefined, and whereas previously children were labeled as mentally challenged, we now have an autistic spectrum that includes a lot of different diagnoses. Here is an article from 2005 after they changed the definition for autism, but you see it's addressing that, the changes in the definition of autism rather than uses of the immunization led to the increased diagnosis of autism. So whereas prior to the change, individuals who were on the spectrum were categorized as something else. But with a revision, more children were identified, and it looked like the incidence went up when it was because of the disease was categorized differently. And so with that, in public health, we look for patterns. What is the endemic incidence of a disease or injury, and is it increasing? Is there a cluster in a geographic area? So in determining the etiology of disease, we need to look at data, analyzed via different types of statistical methods. One of the methods is a correlation. A correlation does not prove cause and effect, but it shows there is a relationship between variables. So in the following video series, we will look at 4 different methods for studying the relationship between the exposure and the development of the disease. 3 of them are observational, with researchers observing natural occurrences, and the last is what we know as a true experiment. So, working from the bottom up, we're going to first talk about group associations. We will then move to the observational methods, being cross-sectional, case control, and cohort studies. And then we'll look at the randomized control trial.